Good day, uni students. I'm Norman Wildberger. Today we're going to look at sets, logic, and graphs, and important terminology associated to those subjects. This is all part of discrete mathematics, which is a very popular subject at the university level these days. Discrete mathematics is interested in finite computational structures, often closely associated to computer science. Alright, so let's start first with some set theory and related data structures. So we're talking about ways of organizing mathematical objects into units, which can then be thought of as mathematical objects themselves. And we'll stick with finite examples at first. Okay, there are actually four types of data structures which are common: the set, the list, the multi-set, and the ordered set. The set gets most of the attention in mathematics, but in fact these other ones are also quite important, and so at least we're going to mention them. So, what is a set? We can say that it's an unordered collection or grouping or combination of distinct mathematical objects. Distinct means they're all different. So for example, here's a set A, consisting of 2, 3, 5, and 7. When we say it's unordered, it means that it doesn't change if we move the objects around. So if we permute them, 5, 3, 7, 2, it's the same set. A set is determined by the particular kinds of brackets that are used, and these brackets are often called braces. And notice that the elements of the set are separated by commas. So the key properties of the set are that the objects are all different, so they're distinct, and that the order doesn't matter. A list is a collection of objects where things are ordered, where the order does matter, and where repetitions are allowed. So in some sense, it's the opposite of a set. Here's an example of a list. And following computer science usage, it's usual to put that in a bracket, a square bracket like this. And here we have the list 1, 2, 3, 4, 5. And in the list, we are not allowed to interchange two elements. We have to stick with this order. But in a list, repetitions are allowed. So we could replace this 5 with a 3. Then we would get the list 1, 2, 3, 4, 3. That would also be a list. Two other notions: the multi-set, which is a lot like a set, but with repetitions allowed. So it's still unordered, but you're allowed to have more than one of the same object inside. It's called a multi-set. And an ordered set is an ordered collection of distinct objects. So it's like a list, but the objects themselves have to all be distinct. So there are really four possibilities, because we could talk about ordered or unordered, and distinct or not distinct. Those 2 times 2, 4 different possibilities are encoded in these 4 types of data structures. And in computer science, they're all important. And in mathematics, though, we historically have tended to concentrate on sets. That's what we'll talk about mostly today. In order to talk about some terminology with sets, let's consider 2 particular sets. A, which is a set 2, 3, 7, 5. And B, which is a set 1, 3, square. So square is some mathematical object. We are assuming that we've already defined what that is, and so then we can form a set with elements 1, 3, and square. Okay, the notation that we use for the things that are inside the set, we call them elements. And we say that 2 is an element of A, written with this symbol. It's like a little Greek E or epsilon. So 2 is in A, means 2 is an element of A, and square is an element of B. The size of a set, for example A, is the number of elements of A. And it's usually denoted by this notation. The set with absolute value bars on either side. That means the number of elements or the size of the set. So here, the size of A is 4, and the size of B is 3. Two important operations with sets are union and intersection. Here is the union of A and B, which is, here's a very important kind of notation that we use. It's the set of X such that X is in A or X is in B. This is a description of a set. It's telling us that we're going to make a collection of all those things X that satisfy this condition, that X is either in A or it's in B. Now this vertical line here, which is a lot like the vertical line that we use there, is sometimes replaced with a colon. Right, so it means exactly the same thing. These are just two different ways of writing the same thing. And so here, again, is how we read this. The set of X such that X is in A or X is in B. These are the conditions. This is the object. So we're talking about the set of objects such that they satisfy this condition. And complementary to that is the idea of an intersection. So A intersect B is the set of X such that X is in A and X is in B. So the elements here have to be both in A and in B. They have to satisfy two conditions. So in our example, the union of A and B would be the set 2, 3, 1, square, 5, and 7. Those elements which are either in A or in B. And the or includes the possibility that they're in both. So 3 happens to be in both A and B. It's still an element of the union. The intersection, A intersect B, is just the set 3. It's the only element which is in A and in B. So a very important idea in set theory is the idea of a subset of a set. So if A and B are sets, then A is a subset of B, and we write A and then this sort of sideways U, B, or A with a sideways U and an equal sign there, B, precisely when X is in A implies X is in B. So let's think about what this means. So more informally, we say that A is a subset of B if whenever we choose an element of A, that element that we chose is also an element of B. Another way of saying it is that all the elements of A are elements of B. These two different notations are equivalent. They mean the same thing. Some textbooks will use this and some will use that. So for example, here's a set 1, 3, 4. Here's another set 1, 2, 3, 4, 5. This set is a subset of this one because every element in this set is an element of this set. The 1 is, the 3 is, and the 4 is. So this is a subset of that. We would not say that this set is an element of this set because it's not. What is true is that every element of this set is an element of that set. In this example, we have a set consisting of geometrical figures, triangle, square, and circle. And here's another set, a triangle, upside down triangle, and some kind of summation sign. In this case, this set is not a subset of this set. Here's how we write not a subset. We put a line through it. And it's not a subset. Why? Because there's an element in this set which is not an element in this set. Which element? A square. So square is an element in this set, but it's not an element in this set. Therefore, this is not a subset of that. And I'll mention this interesting construction of the power set of a set. So if you have a set A, then the power set of A, often denoted this, P of A. What is it? It's the set of all subsets of A. Takes a bit of thinking about what that means. Okay? So the power set of a set is another set whose elements are all the subsets of A. Here's an example. So suppose A happened to be the set triangle, square, circle. All right, then the power set of A is going to be the set of all subsets of A. And this is really useful because we can see all the subsets, what they look like. First of all, there's the empty set. This is a very special set. It's a set which is often also denoted like this, a pair of braces with nothing inside. So it's the set with nothing inside it. It's important to include that as a set, even though you might think it's kind of nothing. It's sort of an analog in the set theory world of the number 0. Number 0 is very important in arithmetic, even though it actually doesn't represent a quantity, except the 0 quantity. Okay, so we have these two different notations for the empty set. They're both used. So the empty set is a subset of A. Here's another subset, just the set consisting of the single element triangle. And here's the set square, the set circle. These are all subsets of this one. Here are the subsets with two elements. The set triangle square, the set triangle circle, the set square circle. They're also subsets of this one. And finally, the set itself is also a subset of itself. All right, so A itself is a subset of A. Altogether, there are 1, 2, 3, 4, 5, 6, 7, 8 subsets of this set A. And that's not too much of a surprise, because if you're going to make a subset, you basically have three choices to make. You can choose whether to include this one or not. You can choose whether to include this element or not. And you can choose whether to include this element or not. So there's 2 times 2 times 2, or 8 possible choices of subsets, corresponding to the choices of take it or not take it. So if you take a discrete mathematics course at the university level, for example at UNSW, that would be Math 1081, then you will learn a lot more about the algebra of sets. But even if you don't take discrete maths, still the language of subsets and elements is used throughout mathematics, calculus, and linear algebra. So the two slides I've shown you are still important even for those other subjects as well. Another kind of discrete maths topic which is often useful in other areas of mathematics is elementary logic. All right. So, which deals with mathematical statements and the relationship between statements and also the truth and false values of statements. It turns out that there's a kind of arithmetic with mathematical statements which is not too far from the arithmetic of sets. Okay, so a mathematical statement is sometimes called a proposition. That's another word for mathematical statements. And in mathematical logic, in this area of mathematics, we like to give these propositions names, say like P or Q, and we treat them as objects on their own, thinking of trying to do a kind of arithmetic with propositions. This kind of arithmetic is sometimes called Boolean algebra. So let's suppose that P and Q are some kind of mathematical statements. Then we can form some related statements from P and Q. First of all, we can look at the negation of P. This is said not P. And sometimes we use a little symbol like this for not P, and sometimes there's a little symbol like this for not P. This is the negation of P. So if P is the statement, it is raining today, then not P would be the statement, it is not raining today. If P is the statement, 1 plus 1 equals 3, then not P would be the statement, 1 plus 1 does not equal 3. So we're considering statements which may or may not be true. Okay? It doesn't really matter at this point whether a given statement is true or false. We can still perform these kind of operations with those statements. We can combine two statements to give a bigger statement in two different ways. One of them is to string them together with an and between them. So this here is P and Q. It's a little bit like an intersection, but it's pointed. And this one here is the statement P or Q. P or Q. So if P is the statement, it's raining today, and Q is the statement 1 plus 1 equals 2, then this would be the statement, it is raining today and 1 plus 1 is 2. While this one here would be the statement, it is raining today or 1 plus 1 equals 2. It's a way of combining two statements to get a bigger statement that contains both of them in some way. Another way of getting a bigger statement is this important implication construction. We write P implies Q. This arrow is a new statement which is stated P implies Q, or another way of saying it, if P then Q. Right? So these two things mean the same thing. P implies Q means the same as if P then Q. And both of them are represented by this symbol. Here is something a little bit stronger. P and then this double arrow Q. There are a number of ways of saying what this means. One is that P is equivalent to Q, that they're basically the same statements or different forms of the same statement. Another way of saying that is this construction. P if and only if Q. A statement that I prefer, another way of saying this is P precisely when Q. A more longer way of saying it is that P implies Q and Q implies P. So this statement here has together inside it sort of two of these. One with P implying Q and the other one with Q implying P. So if both of them are true, then P is equivalent to Q, or P if and only if Q, or P precisely when Q. So these constructions are used in many areas of mathematics. When we want to combine statements, we use these constructions to discuss implication, when one thing causes something else, or when one thing implies something else. Let's have a look at these various constructions in the case of two statements which are sort of everyday statements. So let's say P is the statement, it rains today. And Q is the statement, I get wet. Now let's think about combining them in these different ways. So the statement not P is the statement, it does not rain today. And the statement not Q is, in English, I don't get wet. Okay, we could also say, it's not true that I get wet. But the meaning is the same as I don't get wet. So this is the negation of this statement. How about P and Q? Well, it's the statement, it rains today and I get wet. while P or Q is the statement, "It rains today," or "I get wet." P implies Q. What would that be? If it rains today, then I get wet. Let's have a look at this. This is very important. Okay, so we're combining these two statements with this construction using the words if and then. These are two very important words in mathematics, and you should think about them as coming together. They're like twins. They're like two sides of the same coin. Generally, when you see an if, further down the sentence, there should be a then to match up with it. So if this, then that. That's the basic construction. So if it rains today, then I get wet. Telling us that this proposition implies this proposition. Now sometimes people get a little bit sloppy and they leave out the then. And they might put just a comma here. And they would read, if it rains today, I get wet. In ordinary English, if we would say that, there would be an implicit then. The listener would understand that the word then is implied, but it's just not being used. In mathematics, it's very good practice to try to use the then, to put it in there explicitly so we know exactly what this proposition is and what this proposition is, because they're separated by the then. Here's another way of saying this statement, another way of phrasing it in English, which is a little bit more cumbersome, but it's still important to understand it. It's, it rains today only if I get wet. This is a more awkward statement in English, but mathematically it's important to recognize that it means the same thing as this. If it rains today, then I get wet is the same thing as it rains today only if I get wet. Okay, what about the other way around? Q implies P. Well, we interchange things. So you would read that as, if I get wet, then it rains today. And another way of saying that is, I get wet only if it rains today. And now let's put them together with this equivalence statement. P is equivalent to Q, or P if and only if Q. That would be, it rains today if and only if I get wet. Or I prefer, it rains today precisely when I get wet. This statement is saying, if one of these happens, then the other happens. And it doesn't matter which one happens first. If this one happens, then this one happens, and if this one happens, then this one happens. They both either both happen, or they both don't happen. Now notice this construction here, if and only if, really combines two of these kinds of constructions we were talking about before. So the P implies Q, this one here, is exactly this statement. If it rains today, then I get wet. Or, it rains today only if I get wet. That interpretation is inside here with the only if. And the Q implies P is, it rains today if I get wet. Or, if I get wet, then it rains today. The statement here is really the same as this one. It rains today if I get wet. All right, so these are some different kinds of examples of ways of combining propositions to get other propositions. Okay, so there's another interesting topic having to do with statements, and that's understanding the difference between the converse and the contrapositive of a statement or proposition. So a given mathematical statement or proposition, say P, in practice it may be true, which is usually denoted by capital T, or it might be false, which is usually denoted by capital F. So when we write down a statement, P, it might be true, or it might be false, or maybe it's ambiguous in some sense. Maybe it's not clear whether it's true or false, or it depends on something else. So now here's an important construction that occurs a lot in mathematics, the idea of the converse of an implication. If we have a statement of the kind P implies Q, then the converse of that statement is the statement Q implies P. So for example, if it rains today, then I get wet. The converse of that statement would be, if I get wet, then it rains today. This is the converse of that. The two ingredients are the same, but the direction of implication is reversed. And it's important to realize that these two statements are in general logically independent. Just because one of them is true does not mean that the other one is true as well. All right? So just because you know that P implies Q, you cannot deduce from that that Q implies P. For example, suppose that we know that if it rains today, then I get wet. Let's suppose that's a true fact. We might be out for a walk outdoors, okay, in which case this would be a true statement. If it rains today, then I'm going to get wet. The converse statement would be, if I get wet, then it rains today. That might not be true. I might get wet by some other means. I might get wet by going for a swim. All right? So even if this statement is true, the converse doesn't have to be true. It could be, but not necessarily. Another way of getting a related statement to the implication P implies Q is to take the contrapositive. That's a longer word. The contrapositive of this statement P implies Q is this statement. Not Q implies not P. Now, these two statements are always logically equivalent. If this one is true, then this one is true. If this one is true, then this one is true. Or if this one is false, then this one has to be false, and vice versa. Let's try to understand this through an example. So, if it rains today, then I get wet. So it rains today is P, I get wet is Q, as before. The contrapositive of this is, if I don't get wet, that would be the not Q, then it doesn't rain today. That would be the not P. These two statements are equivalent. If one of them is true, then the other is true. If it rains today, then I get wet. If that's true, then if I don't get wet, it means that it doesn't rain today. So these are two different ways of generating other related statements to an implication. The converse and the contrapositive. And they're importantly different in that the converse is not necessarily logically the same as the original statement, but the contrapositive is logically the same as the original statement. So please have a think about some other examples from daily life and cook up some converse and contrapositive statements. For our third topic today, let's have a brief introduction to graphs or graph theory. So here's an example of a graph. What do we see? Well, we see a bunch of dots, which are called vertices, and we see a bunch of lines joining the dots, which are called edges. So that's what a graph is. It's a set of vertices which are joined in pairs by some set of edges. In this case, this graph is called X. And the vertices are A, B, C, D, and E. And the edges have, in this case, names X, Y, Z, V, and U. Okay, here's another example of a graph illustrating some other things that can happen. So here's a graph with vertices F, G, H, I, and J, and some edges which I haven't labeled, but here's an edge from G to H. Here's an edge from H to itself. That's called a loop. Here's an edge from G to itself. That's also a loop. Here's an edge from G to I, and here are two edges from I to J. So are these kind of things allowed? Yes, they are allowed. Also, here is a vertex which isn't connected to any of the other ones, sort of an isolated vertex. Okay. So a simple graph is a special graph that doesn't have any loops and doesn't have multiple edges. So no loops or multiple edges means we're talking about a simple graph. Theory of simple graphs is particularly pleasant. This is an example of a simple graph. The degree of a vertex is the number of edges that are incident with it, or the number of edges that come into that vertex. So the degree of this vertex C is 3 because there's 1, 2, 3 edges coming into it. The degree of F is 0 because there are 0 edges coming into it. The degree of I, right here, is 3 because there's 1, 2, 3 edges coming in it. We should remark that a graph like this really only depends on the relationships between the vertices and the edges. If we move the vertices around, the essential nature of the graph doesn't change. So for example, if I move this vertex A over here and just move that edge X so that it's from here to here, we would say that's the same graph. It has the same edges, same vertices, and the same relations between which edges connect which vertices. One way of encoding the information of a graph is through an adjacency matrix. So a matrix is an array, a box of often numbers. And in this case, it's a matrix whose rows and columns are labeled by the vertices A, B, C, D, E. A, B, C, D, E. And all the entries are telling us how many edges there are between the two vertices. So this one right here at the position C, B is telling us that there's one edge between B and C. And you see it's got to be symmetric because if there's an edge between B and C, then there's also an edge between C and B. The information of the graph is contained in this matrix. Now, a very interesting concept in graph theory is that of a circuit. It means that we're thinking about a path along the graph that starts and ends at the same point. If you think about the vertices of a graph as being like cities and the edges as being roads connecting the cities, then this is like a Sunday walk where you go from one city to another. Every time you enter a city, you leave it along some different road, and eventually you come back to where you started. That's called a circuit. So it's a path or a sequence of adjacent edges that returns to the starting point. There are historically two important kinds of circuits that are natural to consider. The first one is an Euler circuit, named after Leonhard Euler, who basically initiated graph theory about 250 years ago. So the idea is that we're looking for a circuit that passes through each edge exactly once. So for example, in this graph Y, it does have an Euler circuit, and here it is. Let's see. So we start at H, and then we go to L, and then to J, and then to I, and to M, and then to H, and then down to I, or across to I, and then to L, to K, to J, and back to H. And you can see that indeed we have traversed every edge exactly once, and we've started and ended at the same spot. The idea of a Hamiltonian circuit, very similar, except that we're interested in passing through each vertex exactly once. So this graph X has a Hamiltonian circuit. For example, we start at A, and then we go along here to F, and then we go up to B, and then to C, and then to D, over to G, and then to E, and back to A. We haven't necessarily traversed every edge. For example, we haven't gone along that edge or that edge, but we have visited every city or every vertex exactly once, and we've returned to where we started. It turns out that for a general graph, deciding whether it has a Hamiltonian circuit is rather tricky. Deciding whether it has an Euler circuit is surprisingly simple. If you don't know, you might like to think about how you decide such a thing. Now, the idea of a circuit allows us also to identify a very important subclass of graphs called trees. Here's an example of a tree. It's a very special kind of graph that doesn't have any circuits. There are no circuits in a tree. So there are no closed paths that you can take that will get you back to where you started. Okay. So there's a quick introduction to some aspects of discrete mathematics, sets, basic logic, and graphs. In our next lecture, we're going to look at terminology for calculus. It's of course a key subject for incoming university college students. Hope you'll join me for that. I'm Norman Wildberger. I'll see you all next time.